Hello? Okay. Thanks to the organizer for giving me this chance to present the work I've done with Ryotake Lie in Japan, and also Qixin Ye, who is in the audience. So the last line will be our then references. Of course, this is one of the continuous projects in our collaborations. So I've noticed that I'm bad at citations. So in case I miss any proper references, please ask me later, or you can check in the reference list in our publications. So I figured this is a combined audience of both phenomenologists and string or field theorists. So I tried to make this as simple as possible by giving most of the time in this report as an introduction to matrix models. And for people who are really interested in the main idea, please focus on the last two parts when I get there. So I start with the brief introductions and tell you the motivation why we are doing this and why this is interesting. And then I show you the main contents of matrix models, namely one of the useful way to formulate matrix model is to use fermionic pictures. In particular, that can be interpreted as the eigenvalue of a given matrix. From here, we define what is a landscape, which is one of the key issues in quantum gravities. And the nice thing about a matrix model is that you can give a quantitative descriptions of that. So in the end, I'll give you concrete examples and show how do we construct a landscape in a matrix model. Okay, so sorry again, every string talk contents with some propaganda. So this is to show you why we're interested is because string theory is successful in providing a scenario of quantum gravities, and also matrix model in particular, it's a very simple toy model. So many of the information, in particular the non-perturbative completions and exact correlators, can provide some hint to the more complicated or realistic string theories. So to begin with, this is very simple. Previous speakers speak about 5 dimensions and maybe even higher, but I was very naive, so let's focus on 0 dimension. So this is just calculus. So in this context, I'll talk about the matrix models without any time or spatial dependence. So the ensemble is just given by the usual numerical matrix and with a given weight, which is defined by a potential. Okay. Usually the potential is given as a polynomial form. In this particular context, you can choose a Gaussian part together with higher degree polynomial in the matrix. And the matrix is given by this Cartesian combination, namely if I look at the ensemble of Hermitian matrix, all the coordinates in this path integral is given by these matrix elements. For the comparison with the minimum models or non-critical strings in 1+1 dimension, sometimes it is also useful to introduce Okay, here. Sometimes it's useful to introduce 2 sets of matrices. Here, X and Y are both matrices degrees of freedoms. This is useful because if we wish to map all these matrix computation to the full PQ minimum of strings theory. But in this talk, I'll mainly focus on one matrix model. Okay. There are many ramifications of matrix model that you can see in the literatures and references. For example, you can modify the ensemble, which appears in the functional integrals. Here I denote the ensemble as H. So you can choose Hermitian ensembles or orthogonal matrices and so on and so forth. That could give you different physical models to either string theory or even condensed matter systems. And secondly, you can also modify the integration measures. One of the notable class of these models is called beta ensembles, where in addition to the usual canonical Cartesian measure, you can also include some Vandermonde determinant to some fractional power, which is called for beta. That's why it got its name as a beta ensemble. That is a natural extension to some of these ensemble classes like orthogonal or Hermitian ensembles, because if you choose different class of ensembles, sometimes their Jacobian factors will have different powers. So beta ensemble is like an interpolation of these different classes. And thirdly, you can also modify the, of course, this is the easiest game to play with, that you change the potential forms. And for the application in lower dimensional quantum gravity, this is useful because the quantum gravity not only describes a quantized metric, but also a quantized matter. So in order to give the information or prescription what sort of matters was included in the description of lower dimensional quantum gravities, the degrees or the coefficients in the polynomial is important. And finally, for geometrical purpose, we need to take the double scaling limit to go to a smooth limit. But of course, the fundamental advantage of matrix model is that it can start with all finite calculation, namely finite n or finite string couplings. So then after you do all these calculations, you can extrapolate to the continuous limit. So this is usually called as a non-perturbative construction of string theory in a lower dimension. Okay, so let me first review why this is useful in terms of quantum gravities. As many of you have learned in the field theory courses that, or for example in the Z's book, when you do this path integrals, you can imagine every matrix has two legs. So if you do the Feynman diagram type of calculations, you can define what is the propagator. In a simple matrix model, it's just a double line. But if you have Yang-Mu types, you can have the twisting. Okay, so that can be computed by simply adding a source term. Okay. And also you can introduce interactions by including higher degree interactions in matrices. For example, here I introduce n-cube interactions, also a coupling constant. And that gives you vertices which connect three matrices, and you can glue them together. So from here, as the famous paper by de Hooft in the early 80s, that you can see that once you're doing these matrix integrations, the Feynman diagram looks like a fishnet. And normally it naturally leads to a quantum theory of discrete or random surfaces. But there are other details we need to move on in order to generate a theory of quantum gravity. But here I just illustrate the basic idea. Okay? So now I move to the concrete approach in our work that is different from the geometric perspective I just mentioned, because this is very useful, and also in order to attack or extract non-perturbative informations, this is one of the most competing way as compared with the resurgent analysis pioneered by European group. So as I introduce, okay, this is the potential functions as an integration of actions with weight, and then you can define free energy as a log of potential functions. Usually in the matrix model, we define the correlators in this following ways. So in particular, if you just insert one of these operators, this is called the resolvent. As you can recall in your quantum physics courses, the usefulness of the resolvent lies in that all the eigenvalues give you a poke. That's why I put this in the denominators. And when you do the integration, you can imagine all these poles were joined together to form a cut. So that's the main geometrical idea when I later introduced the spectral curve. If you describe the matrix model quantities, the dynamics of eigenvalue simply focus on the cut structures of the spectral curve. Also, this operator can be imagined as a generating function of the higher weight of matrix model simply by doing the geometrical expansions. So that's why this is also useful in terms of statistical analysis. So if you have multiple correlators, you simply insert many of these resolving at different points of X. And one of the main tool to study the partition function or free energy is to use the center point approximation or mean field. So assuming that the matrix is getting larger and larger, namely as the n goes to infinity, where n is the size of the matrix, you can see that, even I didn't put it out, but in general you can imagine there is a dynamics of the eigenvalue associated with n. So to see that, you can do the mean field approximation, and this is one of the typical equations that the resolvent will satisfy. So the resolvent is simply given by the derivative of the potential minus some regular function, some singular functions, y of x. This y of x will be called spectral curve in this context. And so the information of spectral curve is almost equivalent to that of resolvent, since the potential is given. And in general, the one matrix model describes a minimum model with p equal to 2 case. By that I mean the PQ in the minimum labeling, the labeling of minimum conformal field theories. So in the case of p equal to 2, usually this spectral curve is the hyperelliptic functions. Namely, there is a regular polynomial times a square root of product. So here, this means I have S cuts where the xk stand for the age of each cut. And that's where the eigenvalue resides in. So one can extract the density of the eigenvalues by focusing on where the discontinuity happens inside the cut. So the spectral curve will actually give you the density of the eigenvalues. So that's the main message from these eigenvalue pictures. And why do I call this fermionic? Is because notice that when I do the path integrals, I can really choose different bases to serve our convenience. So even though I start with the definition using the rectangular or Cartesian basis, namely the real part or the imaginary part of the matrices, but it is more useful to represent the matrix in this canonical product form, namely where the capital lambda matrix means the diagonal eigenvalues, and U and U dagger is the eigenvectors, which give you the proper unitary transformation related arbitrary matrix to its eigenvalue. Since the usual weight in the matrix model contains only the trace part or single trace part, so for the singlet sectors, the U is can be considered as gauge redundancies. So you can first integrating out and see what is the effective actions among these eigenvalues. So here comes the physical magic. Why? Usually in matrix model we call this particle as fermions. Because when you really do the integrations over the angular variable, namely the unitary transformation, you will find the van der Waals determinant. Okay? This is a very interesting exercise. I encourage everyone who are interested to do it yourself. So promoting that to the original actions, you can see that since the van der Waals polynomial is a product, and this vanishes whenever two of these eigenvalues collides. If you promote that up to the effective action, you'll get a log. And log 0 is minus infinities. But remember, in the upstairs, we have an extra minus sign. So this gives you a repulsive interactions among eigenvalues. So that's why, in this context, even though we might have a background attractive potential, but the eigenvalue will not condense at a single point. Due to these van der Waals polynomials, or effective interaction, they will try to repulse each other. And in that way, they form a cut. Okay, and I already explained to you, the cut is does appear in the mathematics of spectral curve, and that gives you the information of density of eigenvalue, hence the free energy of the systems. Okay, any questions? So, but there are another useful machinery that we need to use, which is orthogonal polynomials. So this is also very standard in this study of random matrices. So if we imagine the action as a weight, then we can use the Grant-Schmidt processes to define what is the orthogonal polynomials with respect to its weightings. And since I didn't I use the orthonormal conditions. So usually you need to know what is the leading coefficient of each individual orthogonal polynomials. And you can show that because the partition functions include the Vandermonde terms, which can be reshuffled in terms of the orthogonal polynomials. So knowing the leading coefficients for each orthogonal polynomial is very important if you wish to compute the partition functions of the matrix models. Here, this is the explicit formula. Once you know how to compute the coefficient, you can get exact results at finite n for the free energy of matrix model. Okay, so this is the reason why orthogonal polynomial is very important and useful in the studies. But if you care about the larger limit, then this can be massaged into some continuous functions, and the product here will become a simple integration. Of course, you can do the similar things for two matrix models. Okay, and then one of the ways to probe the structure of a orthogonal polynomial is to introduce some ABCD operators, which essentially is like a quantum mechanics position and momentum operator. By momentum operator, I mean the derivative on the position of eigenvalue lambda. Oh, sorry, this is lambda. This is typo. And by position, I mean the product with eigenvalue lambdas. And you can see, because of the special property of orthogonal polynomials, there are some simple recursive relations. And the bottom end of that study is that you can show that, just like quantum mechanics, that the AB matrix will form a Heisenberg algebras, and similarly, you can use that to extract information by solving the recursive relations to get the leading coefficient of orthogonal polynomial. Okay? So this is what I recapitulate what I said before, that the resolvent can be thought as a generating functional, and it gives you information of the density distributions of eigenvalues. And furthermore, there's a useful mathematical fact is that the orthogonal polynomials can be related to the determinant. This is a formula derived by Zixon and Zuper, I think. And from here, you can use the trace log equal to log determinant to relate that information to resolvent. So that's another angles to connecting the resolvent to the orthogonal polynomial. And by taking the continuous limit, you can transform that into the Baker-Artesia systems at the suitable scaling limit, but that's too technical. I try to avoid here. Okay, so now I try to tell you in what sense do we mean the non-perturbative completions of matrix models. First of all, as I said, the spectral curve basically tell you how to distribute the eigenvalues among these real axes if you are talking about the Hermitian ensembles. So usually, for each intervals, we can compute what is the fraction of the eigenvalues in the total amount. So this is the integration of eigenvalues densities. And secondly, by suitable normalizations, you can make that into integers. That will give you the number of eigenvalues within a particular cut. And one of the important conjecture, maybe not conjecture now, it's sort of proved by Ennard, is that he claimed that in the context of matrix models, you can obtain the full non-perturbative partition functions purely in terms of perturbative partition functions in this way. So given any cut, by choosing arbitrary distribution of eigenvalue, this is the number of eigenvalues, you first compute what are the partition functions associated with the perturbative theories. And you weight it by these so-called instant of vigosities and do the all possible sums with respect to the distribution of number of eigenvalues. He claimed this will give you the full information of the non-perturbative information for the matrix model. Okay, so this is a very strong statement. And indeed, if you do the expansion, you'll find all this information look like this. Here, this is the expansion to the first order in theta. So you can see that the first part is the perturbative part. And the second part is what we usually call the instanton contribution. So theta here is weighting factors for each instanton actions. But recall that in the previous page, I didn't tell you how to choose okay. At this level, you only specify the 4 answers to perturbative contributions, and saying that the full answer is simply given by the combination of different distributions. The weighting factor or the fugacity of instanton here is left as a free parameters. Okay. So this context didn't tell you which theta is the best one or the unique one to choose to describe a particular string theory. But so this is why the name is called fugacity, because this induced the interaction of instanton actions. And also, if you do the if you compute the instanton actions in the context of Fermionic pictures, what we mean by instanton is to add one more eigenvalue within a particular cut. So in this case, I specify A. A is one of these. This is a multi-cut scenarios. So you add one more eigenvalue, NA plus 1, and subtract the interaction, the free energies with the original configurations. So that's the eigenvalue interpretation of instanton actions. And you can see by doing this expansion, as I showed before, this was controlled by the perturbative free energy entirely. So this is the generalization of this form will be called topological recursions in the usual application of string theories. But in the matrix model, it was checked in perturbative sector realistically. Okay, so let me just quickly go to the how do we make further implication of resolvent. So here we define these string backgrounds, where Q of P is the function you see before. I wrote R of X. Okay, so P here roughly stands for the eigenvalues, and Q is the dual operator. So the other form of spectral curve is to write this as algebraic relations. Typically, this is given by a polynomial, at least within the context of Riemann strings. So generically, we call the integration of Q as a string backgrounds, phi. So the landscape idea is to see what kind of phi you can get. Okay. Also, I should have emphasized that previously I mentioned that theta is a free parameters in Einer's formulas, but in the context of BA systems or the KP hierarchies, we can make connections of the Stokes multipliers to the theta parameters using these isomorphism deformations. So this is seen through the formula of Riemann-Hilbert integrations, but it's outside the scope of this talk today. So I simply tell the results. Why we are interested in the Stokes multiplier is that once you plug this back into the Riemann-Hilbert proper solutions, it gives you the precise form like the theta expansions of free energies here. So that's why we are interested in Stokes multipliers. And there are certain consistent relations we need to match. And solving this is a non-trivial algebraic task. Okay, so now let's get to the top. What is this landscape? Landscape means that given a spectral curve, if I fix the asymptotic behavior, namely I focus on the essential singularity or poles of these algebraic equations, or I should say the center point of phi, or the pole, the pole of the Q of P. And then doing Lorentz series expansion, these are the leading divergent series. So whenever you fix this and leave the other terms sub-intern arbitrary, that will give you a whole continuous spectrums of the phi. So that's what we mean by landscape in the context of matrix models. So to give you an example, let's see, in the context of minimal string models, usually the algebraic curve is given by the Chebyshev polynomials. Okay, this is well-known results in this field. And if you do the integration, you'll find what is the spectral curve look like. In this particular case, I choose Yang-Lee H. So p equal to 2 and q equal to 5. Here you can see that the first polynomial is of degree 2 and second one is of degree 5. So that curve is given of this form, where there's a single cut. So geometrically, you can imagine this is a genus 0 coefficient. And if you match this with the idea of landscape I just mentioned, you can deform the backgrounds. So here I deform the original root expressions for the spectral curve in this following form by introducing new parameters. Here there are alpha tilde, G1 tilde, G2 tilde, G3 tilde. Or after shifting, there are 3 unknown parameters, alpha, G2, and G3s. And if you insist the boundary condition is fixed, you can show that the 3 unknowns is connected by a single parameter, which I could see here. So C will be the landscape coordinates in this context. Actually, if you see the Riemann paper problems, you can solve the contour in these forms. So here, at each age, I specify what is the slope multipliers. And that gives you the non-perturbative completion of the partition function. They have information. And also, usually here, I have some singular set of this should be set of point. So the deformation can lead to effect by pulling this out, and the original singularity will become a new cut inside these regions. So the map of the landscape of Yang-Lee H is given by these convoluting circles, where I have 3 special junction points. And one of them is given by these standard Chebyshev polynomials. And we found one of the particular value. Of course, this has to be convoluted with complicated of elliptic functions. But in the end, the true vacuums of this system lies in the particular value of C. Here. Okay. So we also use the Riemann problem to compute the actions and decay rate of the false vacuums. So this provides some quantitative description of landscape in the matrix model. Okay. So I stop my talk here and thank you.
Okay, so questions for Chuan-Tsung? So your landscape is not what people talk about the landscape of.
Oh, this is like a.
But you still create a string landscape.
Yeah, because it's like a mini space truncations where I already specify what is the matter content, and the asymptotic condition is the. Usually in field theory, when you say the moduli is the parameter that parameterizes all the physical solutions. So C here stands for the same row. So by tuning C, I'm still getting the solution of the same fixed theories. So that's what I call landscape.
All right. So we visualize the landscape as a lot of mountains.
Okay.
The pictures. It doesn't.
I didn't show you the potential. The potential is defined by calculating the perturbative energies. So if you want to see the mountains, I need to provide you another figures where the horizontal axis is C and vertical axis is some kind of energy.
Okay, so but you do have that sort of a feature. Yeah. Okay, that's what I mean. Your connections maybe in that. All right. More questions? Yeah.
Yes.
Question. Is it possible to introduce a temperature? Something like a temperature, and you can give some
yes.
partition, hexagon partition.
I think so. Yeah, but I haven't gone that far.
Because otherwise it's just a landscape. Right? It's a transition, not string transition. More interesting.
Yes.
Okay, let's thank Chuan-Tsung for the talk.